So I'd like to thank you for the organizers to give me an opportunity to hear. I'm really enjoying this conference. Many interesting talk and motivating discussions and beautiful scenery. So today I'm going to talk about the Lagrangian fibers of Gelfand-Cetlin system. This is based on the joint work with Yoon Cho and Yongguno. So first, let's talk about our playground, the partial flag manifold. So let n be a strictly increasing sequence of the integers. Then the partial flag manifold is a complex manifold. It's parameterized by the nested sequences of complex vector spaces whose dimensions are the given prescribed sequence. So for example, let's think about the F13. That's the complex one-dimensional space in C3. So that's just the CP2. Okay. So we are going to focusing on the Fn, so complete flag manifold. So let me introduce shorthand notation Fn. So Fn denotes just a complete flag manifold. As a homogeneous space, it can be described as a unitary group quotient as follows. Okay. Now here is another description of the partial flag manifold, which will be useful to us. So first, let lambda be a sequence of the real numbers, decreasing sequence of the real numbers. Then let's identify the Lie algebra of the UN with the Hermitian matrix, and then we consider the cojoint orbit of diagonal matrix lambda 1 through lambda n. So down to earth term, or lambda is simply the collection of the Hermitian matrices whose eigenvalues are exactly lambda. Then we can easily see that the partial flag manifold can be identified with O lambda under the conjugate action. Then it becomes a simple acting manifold with a Kirchhoff constant theory of simple acting form. Now, we are going to construct a certain completely integrable systems on a partial flag manifold, more precisely the co-adjoint orbit. So in the following sense. So a completely integrable system is meant to be a collection of real valued continuous functions on X, such that there exists an open dense subset U on which each function is smooth on U, and the differentials are linearly independent and Poisson commutative on U. Okay. Now, to define the completely integrable system, we need to specify the real valued functions. So for that purpose, let's look at the k by k principal minor of the Hermitian matrix in O lambda. Then let's find out the eigenvalues of it, and let lambda kj be the jth largest eigenvalue of it. Okay? And then let's collect all such eigenvalue functions. Then by the Gilman and Sternberg theorem, these forms are actually completely integrable system on the cojoint orbit. So let's look at the example. Let's consider a Hermitian matrix whose form is like that. And this matrix is a member of O lambda whose sequence is 2, 0, negative 2 because eigenvalue of this matrix is 2, 0, negative 2. And then let's find the position of this matrix. Then the position would be 0, 1, negative 1 because let's look at the first times first size submatrix. Then the eigenvalue is obviously 0, so we get 0. And then let's focus on the 2 by 2 size matrix. Let's find the eigenvalue. It turned out to be 1 and negative 1. So the position of this matrix is 0, 1, negative 1. Okay. Now, let me introduce one combinatorial object called the Gelfand-Cetlin pollito. So Gelfand-Cetlin pollito, is simply speaking, is the image of the co-adjoint orbit under the completely integrable system, Gelfand-Cetlin system. And then it is actually the pollito because of the following reason. So by the minimax theorem, these eigenvalue function has to satisfy these inequalities. Okay? Then let's think about the half plane given by these inequality in some Euclidean space and then take an intersection of them. Then you can define some pollito in the Rn. And one linear algebra exercise says that such a pattern can be realized as some Hermitian matrix. So we can fit up all the pollitos. So the image is just the pollito given by these inequalities. So let's look at the example, F3 example, with the sequence lambda 1 through lambda 2, strictly decreasing sequence lambda 1, lambda 2, lambda 3. Then Gelfand-Cetlin pattern would be like that. So inequality is like that. So we have 6 inequalities, and then we have 3 variables. So we're going to think about the half planes in the 3-dimensional space, and then take an intersection of 6 half planes. Then you will end up getting this pollito in the R3 space. Okay. Even if the Gelfand-Cetlin pollito is supposed to be easier than the partial flag manifold, but we will deal with the arbitrarily large dimensional Gelfand-Cetlin pollito. Let me introduce some auxiliary combinatorial object which will be used to describe the phase structure of the Gelfand-Cetlin pollito. Here you go, ladder diagram. So a ladder diagram is the set of the boxes, each of which contains one component of the eigenvalue functions arranged in the anti-diagonal manner. So here is a ladder diagram. So as you can see, in the first anti-diagonal, it contains the eigenvalue of the 1-by-1 principal minor. So in the second diagonal, we have the eigenvalue of the 2-by-2 minor, and so on. And here, the point in the bottom left corner will be called the origin. And a point which is the farthest from the origin will be called the top vertex. Okay. A positive path is meant to be a shortest path from the origin to a top vertex. So positive paths can only go up to the right. Okay. Now let's look at the diagram phase correspondence. So suppose that we have the co-adjoint orbit with a suitable symplectic form. Okay, then we can find the ladder diagram. Okay, and then we are going to look at the sub-diagram of the ladder diagram. That's the one side, and then the other side, we have the image of the co-adjoint orbit through the completely integral system. Then we get Gelfand-Cetlin pollito, and then let's look at the faces on the Gelfand-Cetlin pollito. And by theorem, Byung-Hee An and Yoon-Young Cho and Yoosik Kim says that there is a one-to-one correspondence between the graphs drawn by a collection of the positive paths satisfying certain condition and the faces of the Gelfand-Cetlin pollito. So let me try to explain what a start condition means. So a collection of positive paths is said to be satisfied the star relation if for each top vertex there is at least one positive path from the origin to that vertex. So here is the example F3. So this is the ladder diagram of the F3. And the first graph actually satisfies the start condition because that in this case actually at each top vertex there are exactly one positive path from the origin. Okay? And then this one also satisfies the start condition, but this one does not satisfy the start condition because there does not exist any path to that top vertex. And this one does not satisfy the start condition because that's not the desired graph because that's not the collection of the positive paths. Okay? And so let's briefly explain how to find the corresponding phase if we are given a graph satisfying this condition. So simply, the corresponding phase is defined by the intersection of the facets given by the equating to adjacent variables, not divided by any positive paths. Okay, so we'll see the example in the next slide.
Could you say this picture is okay? Why is that? Vertex.
This one.
Yeah.
This one.
Yeah.
So yeah, we have top.
Pass.
Yeah.
Two passes, right?
Yeah, but there exists at least one pass.
Ah,
Yeah, yeah. So yeah, multiple passes. Okay. Mm-hmm. Any other questions so far?
So which passes correspond to the facets of the, and which passes to the?
Oh, that's a very good question. Yeah, so this is in the next slide. Yeah, okay, yeah. Thank you for asking that question. So, okay, so let's explain some combinatorial data that we can read from the graphs. So first, the data diagram has to be order preserving. So what do I mean by that? So let's look at the graph, and then suppose that one graph is contained and another graph. Then corresponding phase has to be a phase of the second one. Okay, so that's the order that's order preserving means. And then dimension, we can actually read off the dimension from the graphs. So but let's count the number of the simply connected regions in the graph gamma. That's exactly the dimension of the F. So if you want to find the facet, for example, in this case, you should find the graph drawn by the positive path satisfying star condition with two simply connected regions. So for example, this case, this facet, this one is a facet because it contains like the two simply connected regions, so it's two-dimensional. Okay, and then let's go back to this example. Let's look at the F3. The eigenvalue, prescribed eigenvalues are 2, 0, -2. The ladder diagram is here. Let's look at the front face. Front face is actually given by lambda 1, 2 is equal to 0 equation. Supporting hyperplane is lambda 1, 2 is equal to 0 here. And then this, the top edge is given, the corresponding graph would look like that. So this graph, this edge actually is contained in the line segment defined by the lambda 1, 2 is equal to 0 and lambda 1, 2 is equal to lambda 1, 1.
So the dotted line becomes equal.
Yes, exactly. So for a given point in the Gelfand-Cetlin pollito, one can easily tell which phase actually contains it. For example, let's look at this point, 0, -1, -1. So this point this same, so we have to get rid of this positive path, and then we get this graph. This graph is correspond to that. So let's look at another one. Let's look at this example. So 0, 0, 0 point actually has this pattern. So here, so the position of that point would be here. Okay. So that's the diagram phase correspondence. So now we are interested in the fiber of the Gelfand-Cetlin system. Okay, so before explaining the features of the Gelfand-Cetlin fibers, let's give some definitions. A submanifold Y will be called the isotropic if the symplectic form vanishes, if we restrict the symplectic form to that given submanifold Y. And in addition to that, if dimension of the submanifold is happen to be the half-dimensional, then the submanifold L will be called Lagrangian. So here is a quick example of the Lagrangian. So let's think about the complex plane, product of a complex plane with the standard symplectic form. Then, so let's think about the circle in the complex plane and then take a cross product it. Then you can, that's the Lagrangian submanifold. And let's look at the oriented surface with the area form. Then the smooth curve is Lagrangian. Okay. And let's highlight the features of the Gelfand-Cetlin fiber. Let's compare with the usual toric fibers. So it has a similarities like this. So if you choose a one point in the interior of the pollito, they are all Lagrangian torus by the Arnold-Louisville theorem. And then if you choose a point not in the interior, then the inverse image is just isotropic smooth submanifold. That's the similarity. And then here is a key marked difference. So if you choose a point not in the interior of the Gelfand-Cetlin pollito, the inverse image might be Lagrangian. But in the toric moment pollito case, the toric fiber is always k-dimensional torus if that is the inverse image of a k-dimensional stratum. So that's the key difference. We'll look at that example here.
What's the difference between second and third? That they have say not in the interior, not in the interior. What's the difference?
Oh, so that's the similarity of the fiber over the point in the point not in the interior. That's the similarity. That's the difference.
So they are isotropic submanifold, but it cannot be. It can be Lagrangian, but it cannot be Lagrangian.
Exactly.
Dimension.
Exactly.
I see.
So here is an example. So let's look at the complete flag manifold F3 with prescribed eigenvalue 2, 0, negative 2. Then let's look at the fiber of the origin. So that's actually Lagrangian. So let's look at let's see how the fiber look like that. So let's look at the inverse image of 0, 0, 0. Then we have to consider the Hermitian matrices whose eigenvalues are 2, 0, negative 2, and with these information. So what was that? The first component gives us the eigenvalue of the first principal minor. So that has to be 0. We have no option. And let's look at the second 2-byte principal minor. Eigenvalue has to be 0, 0. And that's the only possibility. Okay? And then find the characteristic polynomial and then plug in these numbers, then you end up getting that equation. So that's the 3-sphere. So the inverse image of that origin looks like the 3-sphere, and then it turned out to be Lagrangian. So this motivates us to define the following notion. A face of the Gelfand-Cetlin pollito will be called Lagrangian if it contains a Lagrangian Gelfand-Cetlin fiber at its interior, its relative interior. So natural question would be which face is Lagrangian. So to tell the combinatorial criterion for the Lagrangian faces, so let's introduce some combinatorial object L blocks. So L block should look like that. So it is kind of a collection of uni-size blocks. The width is the uni-size. And one more feature is that the bottom length has to be equal to the height. So that's the 1x1 size L block. That's a 2x2 size L block, 3x3 L block, and so on. And the ladder diagram is said to be L block fillable if L block covers the ladder diagram obeying the following properties. So first two conditions are pretty intuitive. So let's focus on the third one. The blue edge, so what's a blue edge? Blue edge is a top edge and the rightmost edge. So top edge and the the rightmost edge should be mapped into a pieces of positive paths.
The ladder diagram or a face?
Ladder diagram, so exactly speaking, a graph in ladder diagram satisfying start condition. Yes. Mm-hmm. Yeah. Okay, thank you. So the theorem is that a ladder diagram is L block fillable if and only if the corresponding face is Lagrangian. So that's the complete classification of the Lagrangian face. So let's look at the example. Let's look at F7. Let's consider the two following faces. Okay. Then first one is 6-dimensional faces because 1, 2, 3, 4, 5, 6. Yeah, seven dimensional. Yeah, I'm not good at counting. Sorry. So first face is 7-dimensional face, and then second one is 11-dimensional. I believe it's true. Anyway, so 11-dimensional face. Okay. So to apply the previous theorem, you can do a 3D Tetris game. So we have two puzzles here. Now let's start with a very large L block, a 4x4 L block. There's no place to put it in, so let's throw away. And then let's reduce the size, 3x3 is L block. And then we have the place to put them in, and then put it. And then let's reduce the size, and then put them in, and then this unit size block, and then put them in. Then the first one is covered by the L block. Therefore, the first phase is Lagrangian. But the second one is not Lagrangian because these two are not fillable. So see, if you put that unit block into that boxes, it violates the third condition. What is the third condition? So top edge and rightmost edge has to map into the pieces of the positive passes. So, but there's no positive passes here, right? So this one cannot be filled into that part. So this one is not L block fillable. Therefore, second phase is not Lagrangian.
So the condition is if you fill the size K L block, then the lower L block should be always. That's the condition. What's the? Can I see the condition again?
Sure. So the blue edges should be mapped into the pieces of positive paths. Actually, the way of filling the L block is kind of unique. So the order doesn't matter. So I mean to give more like the easy way, to explain a more easy way, I'm starting with the large block and then reduce the size. That's the kind of intuitive way to.
L block size has to be something.
L block size.
You start out with first L block of size 4, but it's not possible. So
right. Here, yeah. So there's no place this put that 4x4 size L block. So throw away. Then reduce the size, 3x3, and then that's the place we can put it. So put them in. So if
you should be able to fill in size, all L blocks of size, certain size, or what?
Just could you repeat your question one more time?
So the size of 4 cannot be filled in, but size of 3 and size of 2 and size of 1 can be filled in.
Yes.
That's what this example says.
Yes.
What does it say, according to your theory? You say this is Lagrangian.
Yes, because I just find one way of fill this layer diagram using the L blocks. So
if the size of 4 cannot be filled in, but size 3, 2, 1 can be filled in.
Yes. L block covered level diagram.
Whatever size in mind.
Yes. No, the size doesn't matter. You can use any size of the blocks. Sorry. Sorry for that explanation. Okay, so now let's switch our gears and let's look at the non-displaceable and displaceable Lagrangian submanifold. So here is the definition of the non-displaceable and displaceable Lagrangians. So what's that? So first let's look at the Hamiltonian vector field. So let H be a time-dependent function, smooth functions on X. Then we can define the Hamiltonian vector field XH satisfying this relation. By the non-degeneracy of the symplectic form, we can always determine such vector field XH. Then let's assume that our manifold X is compact. Then you can consider the diffeomorphism arising from the flow of the XH, which will be called the Hamiltonian diffeomorphism. And a Lagrangian submanifold L is said to be non-displaceable if L and its Hamiltonian perturbation always intersect, no matter what you choose a Hamiltonian diffeomorphism. And otherwise, it's called the displaceable. Okay, so here is a quick example of the non-displaceable Lagrangian and displaceable Lagrangian. So let's look at S2. Then the the equator here, red equator is non-displaceable, other circles would be displaceable. Because Hamiltonian diffeomorphism has to preserve the areas. So, that equator actually bisects the area. So that's the reason why this Lagrangian has to be non-displaceable. So you probably want to ask, why do I care about that non-displaceable Lagrangian? So here is some motivation. So actually the Lagrangian, the existence of a non-displaceable Lagrangian is a kind of evidence for the rigidity of the symplectic topology. So even if L, there's no reason there's no topological reason L and pi L should intersect, but L and pi L can enjoy some intersection property. So that's the kind of symplectic rigidity phenomena. And then also it has Arnold conjecture, which states that a Lagrangian, certain Lagrangian manifold, and then it's let's look at the Hamiltonian perturbation and then assume that they intersect transversally. Then intersection number has to be greater than equal to the sum of the Betti numbers of the L. So that's the celebrated Arnold conjecture. And then also we have the kind of homological mirror symmetry conjecture. So based on the concept, it's a homological mirror symmetry conjecture. So studying Lagrangian submanifold with some deformation data should correspond to the complex vector bundles over the dual complex manifold. So studying Lagrangian submanifold is a very fundamental object, should be very fundamental object. And furthermore, non-displaceable Lagrangian kind of gives us a candidate for the generator set of the Fukaya category in the A model size. So that's the motivation why we are interested in the non-displaceable Lagrangian submanifold. And then let's ask which Lagrangian Gelfand-Cetlin fiber is non-displaceable. So that's the natural question. And there are at least three known things in this business. So Antolf and Polterovich's non-displaceable Lagrangian theorem says that non-displaceable fiber theorem implies that the existence of at least one non-displaceable Gelfand-Cetlin fiber on a Gelfand-Cetlin system. And actually, Nishino, Nohara, Ueda calculate the flow cohomology, and then they show that there exists at least one non-displaceable Lagrangian Gelfand-Cetlin torus fiber on a Gelfand-Cetlin system. And recently, Nohara, Ueda show that there exists exactly one non-displaceable Lagrangian Gelfand-Cetlin U2 fiber in Grossmanian 2-4. Okay, so these are the known things. And I want to investigate the non-displaceable Lagrangian Gelfand-Cetlin system in a complete flag manifold in more details. That's what I want to do. So let's start from the F3. O lambda identified with O lambda with lambda is equal to 2, 0, negative 2. That's actually monotone complete flag manifold. Let's look at the Gelfand-Cetlin polytope look like that, and then let's look at the very center of the polytope. The component data is here, and then let's look at the position where the Lagrangian 3-sphere is sitting over, and let's think about the line segment connecting them. Then Perbignac's recent result says that all Gelfand-Cetlin fiber, but the fiber over the red lines are displaceable. She proved that statement using the McDuff's proof method and the homogeneity of the flag manifold. Then our theorem says that the Gelfand-Cetlin fiber over each point in the red line is non-displaceable. So combining her work, this gives us a complete classification of non-displaceable and displaceable Gelfand-Cetlin fiber in F3. And in particular, our theorem also implies that the non-displaceability of the Lagrangian 3-sphere here. Actually, Nohara Ueda calculate the flow cohomology of this Lagrangian 3-sphere. It turned out to be 0. So their result does not imply the non-displaceability of the Lagrangian 3-sphere, but our result can. So let's raise the dimension. Let's look at the Fn. Okay? So let P be the center of the Gelfand-Cetlin pollito. We are going to look at the center of a certain Lagrangian phase, corresponding the collection of positive passes having the row left n by n box. What do I mean by this? So let's explain this statement by example. So let's look at Fa. Then we have the 2 by 2 boxes here, and then 3 by 3 boxes here, and then 4 by 4 boxes here. And as you can see, this one is L block fillable. So these are the Lagrangian. Let's look at the very center of that Lagrangian phase. That's a component data of the very center of the Lagrangian phase. And then these are P2, P3, P4. And our result is that every Gelfand-Cetlin fiber over the line segment connecting the very center of the polytope and then center of the certain Lagrangian phase is all non-displaceable. So here is a schematic picture of the position of the non-displaceable Gelfand-Cetlin fiber in F7. So in the very center here has Lagrangian phase, and then connect them. The fiber over this line segment are all non-displaceable.
What's the capital P?
Capital P is the center, very center of the Gelfand-Cetlin polytope. Okay. So here, in this example, P is here. Okay, so I have 10 minutes. Okay, so let's give the idea of the proof. To explain the proof, I have to explain a little bit of the flow theory. So let's do that. Let me try to do that. So let lambda be a Novikov field of the field coefficients. So it's basically a collection of the elements looking like the power series. Okay, but the difference is that the powers are required to be the real number without any accumulation point. So that's the Novikov field. So here, t variable is kind of formal variable. So that formal variable will be used to record the area of some pseudo-holomorphic curves. So that's the area recording parameter. And then also we are going to consider the Novikov ring, lambda plus and lambda 0. So we are looking at the element of Novikov field with a positive exponent and then non-negative exponent. So let's give the one slide for the idea of the Lagrangian flow theory. So to prove the Arnold conjecture, so flow construct the flow complex. So we'll think about the flow complex, a chain complex generated by the intersection point of Lagrangian L and its Hamiltonian perturbation. So let's assume that L and pi L intersect transversally, and the boundary map will be boundary map will be defined by counting certain moduli space of the pseudo-holomorphic strip. It's looking like that. Then if the del squares happen to be 0, then we can define the flow homology. Then one more step would be the flow homology is actually isomorphic to the usual the homology of the Lagrangian. Then we can get the result because the rank of the flow homology is equal to rank of the usual cohomology L. That should be less than equal to the rank of the flow complex. What was the rank of flow complex? That's exactly the intersection number. So intersection number has to be bounded by the usual the rank of the usual Lagrangian homology of L. Then actually this condition is satisfied if that under that condition, for example. So, but in general, flow cohomology may be obstructed or can be 0. Then Fukaya-Ota owners deformed flow cohomology can sometimes resolve these issues. So let's look at the flow cohomology. So we're going to use the same flow complex, but we're going to deform the boundary map. So as follows, let's insert some boundary markings, and then let's fix some designated cycles on the L and its Hamiltonian perturbation, and then require that these blue marked points pass through the B prime. These red mark pass through the designated cycle B, and then think about the all possible insertions and then sum them up, then you can find the deformed boundary map. And then again, if deformed boundary map happens to be 0, then we can define the flow cohomology, deformed flow cohomology. And then let's focusing on the Toric manifold case. This is kind of the well-known example where the calculation is possible. Calculation is somehow achievable. So let X be a compact symplectic Fano-Toric manifold. Then we can define the following Hurry-Bapa and Giventhal potential function. What's that? So the potential function is given by this relation. Here, the VF is a primitive normal vector to the facet, and then LFU is kind of defining equation of the facet. So here is the example, CP2. Moment pollito is looking like that. The potential function is here. In this case, we have 3 facets. The term has the number of terms should be 3. Okay. Then let's look at the first term. So first term actually coming from this facet. This facet. So what's the primitive normal vector? This is 1, 0. So y10 is y1. Okay? And then T LFU. LFU is defining equation of this facet is u1 is equal to 0. So we get y1 tu and so on. Okay? And by the theorem of Cheon-Cho and Yo and Fukaya Taono, then if this potential function admits a critical point at u, then there exists some deformation parameter B, deformed flow cohomology becomes isomorphic to the usual homology of the Lagrangian torus L. So in particular, we can conclude that toric fiber over U is non-displaceable. So let's focus on the CP2 example again. The potential function is look like that. And then let's choose a very center, 1/3, and then 1/3. And then let's plug in that data into the U1, U2 coefficient. Then we get 1/3, 1/3, and 1/3. Then the potential function is arranged as follows. Then you can easily see that critical point of this potential function is 1/3 and then 1/3. Take a y1 derivative, take a y2 derivative, then we get 1/3, 1/3 as a critical point. Therefore, toric fiber is non-displaceable. So let's move on to our Gelfand-Cetlin system case. Actually, Nishino, Nohara, Ueda calculate the potential function. So potential function of the Gelfand-Cetlin Lagrangian torus fiber can be calculated as a toric fiber cases. So let's focus on the F3 cases. So in this case, moment pollito, the Gelfand-Cetlin pollito is looking like this. Then potential function can be written as this one. So we have to think about the 6 possibilities because we have 6 facets, and then read the primitive normal vector, and then write down the potential function, and so on. And that's the exact potential function. And one more step. So I'm going to use the Berkeley deformed flow theory to achieve the goal. What is the Berkeley deformation? So actually, in the previous slide, so we look at this one, right? So I just explained this one, but we kind of insert the interior marker point and then choose a ambient cycle of the symplectic manifold, and then require that these green mark points pass through that ambient cycle. You can actually further deform the flow theory. That's the Berkeley deformed flow theory. Then Fukaya Taono's result says that if the Berkeley deformed potential function admits a critical point, then again we can achieve the non-displaceability of the Lagrangian L. So what I'm going to do is, we're going to use a Schubert cycle of the degree 2 to deform the Lagrangian flow theory. So here is a result of the Kogan and Miller. The Schubert cycle actually are represented by the inverse image of a certain union of faces. So in the Gelfand-Cetlin system case, actually, so here is one facet. So and then the other facet is here. If you just look at the one inverse image of one facet, that's not a cycle. Because as you can see, as you've already seen, there are Lagrangian 3 spheres over this point. And then this is a four-dimensional stuff. Then the boundary actually appears, three-dimensional boundary appears at here. So the single facet may not represent a cycle, but their result said that if you do the some miracle combination, then they will represent a cycle. So you can actually find using the pipe diagram or reduced RC diagram to check whether which phase represents the cycle. So here is a rough picture. So in the ladder diagram case, their result can be interpreted as a vertical Schubert cycle, vertical Schubert divisor and then horizontal divisor. I'm going to use that cycles to deform the flow theory. And one more technical step is this. So after finding the bulk deformed potential function, we need to find the critical point and suitable bulk deformation parameter. But, solving the many variable equation are not an easy task even if we get some aid from the computer program. So, but the combinatorics, my guideline is that you can use guide of the combinatorics to find the critical point of the potential function. So here is the rough picture of what I do. So let's just split the gradient of the potential function into two pieces, depending on the line segment. So in this case, the line segment connecting P and P2, and then decompose into two parts, and then solve this part, and then solve the remaining part, and then graphing the solution, then we can get the potential function. That's the very brief outline of the proof. Okay, so thank you very much.